Hello, my name is Michelle Dang, and this is my ENME 351 Lab 8 makeup lab. So pretty much what this is, I'm following the comparator circuit right here. I even show here just like an example of the different, schematic for the circuit that I built here on my breadboard. So pretty much the voltage divider with these two resistors go into the negative input, which is the inverting terminal, and the potentiometer then goes to the non-inverting terminal. And just besides the ground connection and voltage connection, I also have the output going into the LED, which then shows from when the potentiometer goes all the way to 0 volts, it's at a low output, and when it goes all the way to 5, it's at a high output. And that's just pretty much how this comparator circuit works. When the difference is between the inverting and the non-inverting is all the way to 0, it's at a low input, and when it goes to high, the difference is greater and it goes to a high output.
In exercise 2, we're pretty much asked to mimic a unity gain amplifier into our circuit, and I also have like a schematic here where I show the different connections that I had, the potentiometer going into my non-inverting input, and my inverting input being connected to my output. And as you can see here, that's pretty much just what I did with my circuit, having it go into the op amp. So when the potentiometer is set at a high voltage, V out pretty much moves unanimously with the independent V in that we are controlling, which is the white dots. And then once it goes, V in is pretty high, it's a low impedance, and it's a high current, meaning the values just move pretty consistently with one another. And when it goes low enough, there's a higher resistance and a lower current, which then has V out, mainly outputting the values that are caught from the inverting input and not so much the potentiometer. And if you can see, when V in is the independently moved by our potentiometer values, when it's all the way at 0, it hits like a low bandwidth of the voltage output that we are given, and then once it hits and it passed that, we can see that they move unanimously. And we can also see that V out, as well as the inverting input, since it's a negative feedback, it always pretty much moves unanimously as well. In exercise 4, we're asked to build an integrating amplifier, which is very similar to the inverting amplifier, except with 2 resistors, we have a resistor and a capacitor. The inverting amplifier works pretty much as V in increases and it reached that offset of 2.5 volts. The voltage V out then inverts, and same happens as it goes down. Similar to exercise 3, we are asked to build an integrating amplifier where instead of there's 2 resistors, there is a resistor and a capacitor, as well as the 2.5 offset for the voltage divider, such as shown here. And this is just how the values are derived. We use nodal analysis to get the integrating equation for V out. And similar to exercise 3, the circuit produces an output voltage pretty much proportional to the integral of the input voltage. The difference between this and the inverting is just that V minus is pretty much closer to V in, just because the capacitor is uncharged and there's pretty much little to no resistance between the two, giving V out a pretty high voltage. But once V in passes 2.5, you can see that the capacitor then charges and resistance increases, which makes the voltage lower. Same happens for when it goes down and it's passing 2.5 again. You can see that the
capacitor discharges and resistance decreases, which allows, once again, a higher voltage.